Hello students, and welcome to this 10th lecture of the heat transfer course EEAQ 3235. And in this lecture we are going to have a look at heat exchangers. So let us first answer the question, what are heat exchangers? Heat exchangers are thermodynamic equipments that enables the heat transfer between two fluids that are separated by a solid surface. And these two fluids are in a relative motion to one another. Now, we have a number of ways in which we classify these heat exchangers. One of them is by construction, right, where we may have shell and tube heat exchanger, plate and nerve frame heat exchangers, etc. The other classification is by the way in which the two fluids are flowing relative to one another, and that is what we'll be focusing on in this lecture. So we have fluids where we have fluids flowing in the same direction relative to one another, and these types of heat exchangers are called parallel flow heat exchangers. If one of the flows is reversed, then we have a counterflow heat exchanger. We have another class of heat exchangers that is very important to chemical engineers, that is the cross flow heat exchangers, where the flow of the two fluids is at 90 degrees relative to one another. I have an example of a shell and tube heat exchanger here, whereby you have one of the fluid flowing through that inlet and coming out at that outlet, and the other fluid flowing through that inlet and coming out at that inlet, thereby exchanging heat inside there. Okay, so one of the fluid is flowing through some set of tubes, and the other fluid is flowing in the rest of the bulk of the heat exchanger. Now, bearing that in mind, let us have a look at what a parallel flow heat exchanger and a contraflow heat exchanger is about. So we have an example there of a parallel flow heat exchanger and a counterflow heat exchanger there. Now, for the sake of analysis, we'll take one of the flows, that is the parallel flow heat exchanger or the contraflow heat exchanger, and do our analysis. And you should bear in mind that it does not matter which one you take. The final equation that you come up with will be the same. So the temperature gradient for a parallel flow heat exchanger between 2 points or 2 sections, section 1 and 2, is as shown there. The temperature of the hot stream reduces from TH1 to TH2, and the temperature of the cold stream increases from TC1 to TC2. For the sake of analysis, we'll take an infinitely small section of that exchanger such that its heat transfer area is a dA. So let us take an infinitely small section of the exchanger such that its area is equals to dA. Now we have assumed, or we have said that our first assumption is that the solid surface offers no resistance to heat flow by conduction. The second assumption that we will make, we have adiabatic conditions. Which implies that the heat lost by the hot stream is exactly equal to the heat gained by the cold stream. What is the amount of heat lost by the cold stream, by the hot stream? For the small section, that will be a very small heat loss, dQ, which is equals to the mass flow rate of the hot stream times the Cp of the hot stream times the change in temperature, small change in temperature of the hot stream. And from the conditions that we've imposed, adiabatic conditions, these would exactly be equal to m dot C for the cold stream, Cp C times a dt C. Now if you take the mass flow rate of any matter multiplied by the Cp of the same matter, this is what we refer to as the capacity or the capacitance, the capacity of the matter to store and hence transport heat. And if that is the case, then it means that m dot h Cp, h can be denoted by the capacitance or the capacity C of the hot stream, and m dot C Cp C by CC, such that now our dq is equals to CH dTH, which is equals to CC dTC. And from this equation you can see, or we can deduce, that a dTH is equals to dq over CH, and a dTC is equals to dq divided by CC. So subtract dTC from dTH. So dTC from dTH, this would be equal to dq over CH minus a dq over CC. But there is one thing that we should have noted. That is, if the gain, the direction of gain is positive, the direction of a loss is negative. So we should have added a negative sign there. So we should have added a negative sign there. So this is supposed to be minus dq over CH minus dq over CC. So it means, and now that a dTH minus a dTC is equals to minus dq into bracket 1 over CH plus 1 over CC. Now, the heat transfer by convection is given by the overall, or let's say H times A times of the change of the temperature difference times the temperature difference between the hot and the cold stream. Now, so this is equals to HA TH minus RTC. Now let us have a look at what we call the overall heat transfer coefficient, and we'll look at a simple two-layered wall. So we have a resistance there, another resistance there, a resistance to heat flow by convection there, and resistance to heat flow by convection on the other side. So let us say this is HI, and the heat transfer coefficient there is HO. So supposing that thickness is delta X 1, and that is delta X 2, and the conductivity there is K1, conductivity K2 there. So we've seen that the total resistance R is equals to resistance 1, resistance 2 plus, so it is equals to the sum of resistance 1, resistance 2, resistance 3, and resistance 4. So R total is equals to R1 plus R2 plus R3 plus R4. So this is equals to 1 over HI plus delta X over K1 plus delta X2 over K2 plus 1 over H naught. So supposing now we applied our assumption that there is no heat flow, or there is no heat resistance, or there is no resistance to heat flow by conduction. So that will reduce to R is equals to 1 over HI plus 1 over H naught as our total resistance. And now the heat flow Q, and since there is no heat flow by, there is no heat resistance, or the heat resistance, the resistance to heat flow by conduction is 0, then we can as well say this reduces to a convective heat transfer problem, only Q convection, and this will be given by the temperature difference between the inside and the outside divided by the total resistance R, which is equals to Ti minus T naught divided by 1 over Hi minus 1 over, or plus 1 over H naught. Now 1 over R is referred to as the overall heat transfer coefficient, such that our Q is equals to the area times the overall heat transfer coefficient times Ti now minus T naught. So U here is equals to 1 over R, and 1 over R is equals to 1 over Hi plus 1 over H and naught. So bearing that in mind, we can say that our dq, not our dq but our dq is equals to U times the small area dA times delta T, and that is our second equation. All right, so we can substitute for dq in equation, let's see, in equation in this equation here, all right? So we have dt H minus dt C is equals to dq minus, and we've seen that dq is equals to u dA times delta t, and this is multiplied by 1 over ch plus 1 over cc. Now if you look at the left hand side of our equation, seems that we got this from th minus tc, the derivative of that, and supposing we called this theta, that is th minus tc, then the derivative of this would be equal to d theta. Okay, so we have d theta is equals to minus u dA, and this delta t, all right, which is also theta, is th minus tc. So this is also times theta 1 over ch plus 1 over cc. Okay, so putting or reorganizing the expression, we have d theta over theta is equals to minus u dA into bracket 1 over ch plus 1 over cc. Integrating the expression between section 1 and 2, we'll have integral from 1 to 2 d theta over theta is equals to minus u into bracket 1 over ch plus 1 over cc. All of that is a constant times the integral of dA from 1 to 2. So what is the integral of d theta, or of 1 over theta d theta? That is ln of theta. So supposing at 1 we have theta 1 and theta 2, this is equals to minus u 1 over ch plus 1 over cc. The summation of all areas, small areas between 1 and 2, is the total area A. So that gives us our expression, that is ln of theta between theta 1 and theta 2 is equals to that. So this boils down to ln of theta 2 minus divided by theta 1 is equals to minus ua 1 over ch plus 1 over cc. But Q is equals to the mass flow rate of the hot fluid times its specific heat capacity times the temperature change of the hot fluid, which is TH1 minus TH2, which is also equal to TH1 minus TH2. So from this you can see that our 1 over CH is equals to TH1 minus TH2 divided by EQ. The same amount of heat, Q, is gained by the cold stream, which is equals to M dot Cc times T cold 2 T cold 1. Okay, and such that 1 over Cc, because this is Cc is equals to Q, is equals to Tc2 minus Tc1 divided by Q. So substituting for 1 over Cc and 1 over Ch in our equation, we have ln of theta 2 over theta 1 is equals to minus UA into bracket TH1 minus TH2 over Q plus T equal to minus T equal 1 over Q ln theta 2 over theta 1 is equals to minus UA into bracket TH1 minus TH2 plus TC2 minus TC1. So ln theta 2 over theta 1 is equals to minus U A over Q into bracket, can put TH1 and TC1 together, and TC2 and TH2 together, and I'll put this as a minus such that TH2 becomes a positive and TC2 becomes a negative. Okay, now you can see that TH1 minus TC1, immediately recognize that that is equals to theta 1. So this is equals to theta 1, and that is equals to theta 2. So we can put our equation as ln of theta 2 over theta 1 is equals to minus UA theta 1 minus theta 2. Taking the negatives inside, we have this is equals to UA theta 2 minus theta 1. And there is a Q there. So it implies that our Q is equals to UA theta 2 minus theta 1 divided by ln theta 2 by theta 1. And this is what we refer to as the logarithmic temperature difference, abbreviated LMTD. So our Q is equals to UA times the LMTD. And from that fact, you find out that that is why this method is referred to as the LMTD method. Now, when the entry and outlet conditions are known, the analysis by the logarithmic mean temperature difference method is the method of choice. But you find that when you are required to determine the conditions, maybe at the entry or at the outlet, then the method of the number of transfer units, abbreviated as NTU method, stands in good stead. So this is what we're going to look at now, and we'll start by having a look at what we refer to as heat exchanger. Effectiveness, abbreviated as denoted by epsilon, which is defined as the actual heat transfer divided by the maximum possible heat transfer. Okay, so this is equals to Q, the actual, divided by Q minimum or Q maximum. Now the actual transfer Q is equals to m dot Cp Th1 minus Th2 which is equals to m dot c cpc tc2 minus tc1. So this is the same as th1 minus th2, which is equals to tc2 minus tc1. Now, by comparing cc definitely there will be one that will be bigger than the other, and the one that is bigger than the other, we'll call it a C maximum, yeah, the bigger, and a C minimum, the smaller. So C minimum is the maximum, is the minimum fluid heat capacity, and C maximum is equals to the maximum fluid heat capacity. Now, to determine the maximum possible heat transfer for the heat exchanger, we first recognize that this maximum can only be attained if one of the fluids has to undergo a temperature change equal to the maximum temperature difference available. And the only fluid that can experience this maximum temperature difference is the one with the minimum fluid heat capacity. So Q maximum is equals to m dot Cp, which is a minimum, times the maximum temperature difference available, and that is the temperature of the hot stream at the inlet minus the temperature of the cold stream at inlet. So Th1 minus Tc1. So it means that our epsilon is equals to Th1 minus Th2 divided by C minimum Th1 minus Tc1, which is equals to Cc Tc2 minus Tc1 all over C minimum Th1 minus TC1. When C minimum is known, then we have our Q is equals to epsilon C minimum TH1 minus TC1. So there is an or here. Yeah, it can either be that or that, and when we know the C minimum, then it means we can go ahead and calculate or determine our Q, and our Q is equals to all that. Now let us have a look at the case for a parallel flow heat exchange. We know that dq is equals to u dA th1 minus tc1. So this is equals to mass flow rate of H times CPH dTH, which is equals to m dot CPC dTC. So this is equals to minus, there's a minus there, minus CH dTH, which is equals to CC dTC. And we went ahead and saw that dt minus tc is equals to minus dq 1 over cc ch plus 1 over c. So dt minus tc is equals to minus uda by substituting dq with a duda th minus tc 1 over ch plus 1 over cc. So when we integrated the expression, we got ln of th2 minus tc2 divided by th1 minus tc1 is equals to minus ua 1 over ch plus 1 over cc. So ln of th2 minus tc2 over th1 minus tc1 is equals to minus ua. I'll bring ch outside there such that I'll have 1 here and then I will have plus CH over CC down there. Now this is the same as saying TH2 minus TC2 over TH1 minus TC1 is equals to E, that is the exponential, of minus UA over CH into bracket 1 plus CH over CC. But we've said that the effectiveness is equals to CH TH1 minus TH2 divided by C minimum TH1 minus TC1 can also be equal to CC TC2 minus TC1 divided by C minimum TH1 minus TC1. So from this equation you can see that H2 is equals to TH1 minus epsilon C minimum TH1 minus TC1, and also you can see that this is that is TH2. Can as well see that TC2 is equals to TC1 plus C minimum TH1 minus TC1. That is by taking this expression there. So if you take this part of the equation, this one, and make TH2 the subject, you get that. If you take this part of the equation and make a TC2 the subject, you will get that. And then we can substitute for TH2 and TC2 in this equation here. So we substitute for TH2 and TC2 in this expression here. So we'll have instead of TH2 we'll have TH1 minus epsilon TH1 minus TC1, and we're subtracting from it TC2, and TC2 is TC1 plus epsilon C minimum th1 minus tc1. Okay, and okay, there is a ch here and a cc there, so over ch there, and there is a cc there, divided by th1 minus tc1, and that is equals to the right hand side of our equation, and the right hand side of our equation was exponent of minus ua over ch into bracket 1 plus ch over c, something like that. So we have th1 minus tc1 by removing the brackets, minus c minimum th1 minus tc1. Okay, then I have 1 over ch plus 1 over cc, that way, all over th1 minus tc1, that is equals to the exponent of minus ua, exponential ua over ch 1 plus ch over cc, something like that. So we have as you can see, that cancels out with that and that, so we're left with 1 minus c minimum 1 over ch plus 1 over cc is equals to minus ua over ch 1 plus ch over cc, something like that. Okay, and making epsilon as the subject, you will get epsilon is equals to 1 minus exponential minus ua over ch 1 plus ch over cc, all of that divided by c minimum 1 over ch plus 1 over cc. All right. So if, let's say, cc is greater than ch, Then we'll have C minimum will be equal to CH, and C maximum will be equal to CC. And our epsilon for that case, it will be 1 minus exponential minus UA over C minimum 1 plus C minimum divided by C maximum all over 1 plus C minimum over C maximum. If on the other hand we have CH being greater than CC, then it will mean that C minimum is equals to CC and C maximum is equals to CH. And for that case, you'll have epsilon is equals to 1 minus exponential into bracket minus UA divided by C maximum 1 plus C maximum over C minimum over 1 plus C minimum over C maximum. So we'll have similar equations, right? We are quite similar. And we can say that UA over C minimum is a dimensionless number called NTU, and C minimum divided by C maximum is another dimensionless number called capacity ratio, denoted by R. So you find that our E or epsilon is equals to 1 minus exponential minus NTU 1 plus R divided by 1 plus R. Now if we repeat the same procedure for a counterflow, you'll get our epsilon is equals to 1 minus exponential minus NTU Instead of 1 plus r, you'll have 1 minus r divided by, divided by 1 minus r exponential minus NTU 1 minus r. So we have looked at the LMTD method and the NTU method. So now let's have a look at some examples. So let us have a look at some three examples. And the first example reads: a counterflow double pipe heat exchanger is using superheated steam to heat water at a rate of 10,500 kilograms per hour. The steam enters the heat exchanger at 200 degrees C and leaves at 130 degrees C. The water enters at the exchanger at 30 degrees and leaves at 80 degrees respectively. You've been given the overall heat transfer coefficient as 840 watts per meter squared Kelvin. It is required of us to A, calculate the heat transfer area, and B, to calculate the increase in area if now the fluid's flow were parallel. So now let's have a look at and the solution is, first we look at the mass flow rate of water, which is equals to the mass flow rate of the cold stream, which is equals to 10,500 divided by 3,600, which gives 2.917 kilograms per second. Now TH1 is equals to 200 degrees C, TH2 is equals to 130 degrees C, TCO1 is equals to 130 degrees C. No, not 130, it is equals to 30 degrees C. Is equals to 30 degrees C. And TC2 is equals to 80 degrees C. Now we are told that U is equals to 814 watt per meter Kelvin. So let's have a look at our heat exchanger. So we have, it is a counterflow. So we have a fluid flowing like that, and the other flow being like that. Something like that. So we have so supposing this is our hot stream, that is the hot stream, and the temperature is 200 degrees there. The temperature is 130 degrees C there. For the cold stream, the temperature is 30 degrees there, and this is 80 degrees centigrade there. So let us call this, okay, there, that is 200 degrees minus 80 degrees, which is 120, and compare it with this, which is 130 minus 30, which is equals to 100. So this one is less than that, so we can call this theta 2 and this as theta 1. So, and we know that our LMTD is equals to theta 2 minus theta 1 over ln theta 2 over theta 1. So this implies that our LMTD is equals to 120 minus 100 divided by ln of 120 over 100, and that will give us a figure of 109.7 degrees C. Let us have a look at a case whereby now the flow is parallel again. So again we have 200, 130, and then we have 30 and 80 degrees there, 30 and 80 degrees there. So 200 minus 30 is equals to 170, and 130 minus 80 is equals to 50. So this is our theta 2 and this is our theta 1, and the LMTD now will be equal to 170 minus 50 divided by ln of 170 over 50, and that is equals to 98.05 degrees C. So with those two LMTDs, let us have now a look at the first case when the flow is counterflow. So this is equals to UA LMTD. So we have 2.917 times 10 to the power of 3 times CP 4.187 times the temperature difference of the cold stream 80 minus 30. That must be equal to U 814 times the area which we're looking for times 109.7, and that will give us an area of about 6.84 meters squared. For the parallel flow, we can repeat the same procedure, but you concur with me that it will be equal to 6.84 because nothing else is changing other than the LMTD. So times 109.7 divided by 98.05, and that is equals to 7.65 meters squared. Therefore, the increase that we are after in area is equals to 7.65 minus 6.84 divided by 6.84 times 100, and that gives us 11.8. So let's have a look at the second example. And the second example reads: air is to be cooled in a counterflow heat exchanger from 540 degrees to 146 degrees C at the rate of 12.5 kilograms per second. You're told that the heat exchanger contains 4,600 tubes, and each tube has a diameter of 30 millimeters. You're told that the inlet and the outlet temperature of the cooling water is 25 degrees and 75 degrees respectively. You are told calculate the tube length required for this duty, given that the Nusselt number is equals to 0.023, Reynolds number raised to the power of 0.8 times the Prandtl number raised to the power of 0.4 for this kind of flow. You're told that rho is equals to that, Cp is equals to that, mu is equals to that, and K is equals to that. So we can now look at the solution. And the solution is, first, let us look at the Reynolds number, which is rho V D divided by mu. But note that we've been given the mass flow rate, and we know that a mass flow rate is equals to the volume flow rate times the density. So the volume flow rate times the density, and the volume flow rate is equals to the cross-sectional area A, or let us use capital A, the cross-sectional area, times the velocity times rho. So this is equals to rho A times the velocity v. Now this is just for one, so for n number of tubes it will be equal to rho AV times n for n number of tubes. So from this we can determine our rho V, which is equals to the mass flow rate divided by the area times the number of tubes, and that is equals to 12.5 the mass flow rate times 0.03. Okay, so we can calculate the Reynolds number. The Reynolds number will be mass flow rate times a D divided by AN times mu. So this is equals to 12.5 times 0.03, which is the diameter of each tube, divided by the number of tubes, which is 4,600, times pi by 4 times 0.03 squared times mu, which is given as 2.075 times 10 to the power of -5, and that gives us a Reynolds number of 6,087.4. Let us determine the Prandtl number, and the Prandtl number is mu Cp divided by K, which is equals to 2.075 times 10 to the power of -5 times Cp 1.0082 times 10 to the power of 3 divided by K 8.003 times 10 to the power of -2, and that is and we've been told that the Nusselt number is equals to 0.023. The Reynolds number to the power of 0.8 times the Prandtl number raised to the power of 0.4. So this is equals to 0.023. The Reynolds number 6087.4 0.8 times 0.6966.4, and that we know it is equals to HL divided by K. So H is equals to K over L times 0.023 times 6087.4 times that. So this is equals to K, and K is 3.003 times 10 to the power of negative 2 times 0.023 times 6087.4.8 times 0.6966.4 divided by D. This is D. Okay, this is D divided by D, and D is equals to 0.03, and that gives us a H that is equals to 21.2 watt per meter squared Kelvin. Now the overall heat transfer can be found from this, which is equals to 1 over 21.22. Now LMTD is equals to 540 minus 75 minus 146 minus 25 divided by ln 540 minus 75 divided by 146 minus 25. That is equals to 255.5 degrees C. So Q is equals to m dot h cp h th 1 minus th 2, which is equals to u a lmtd. So 12.5 times 1.0052 times 10 to the power of 3 times 540 minus 146 is equals to 21.22 times 4,200 times pi times d times LMTD, which is 2525.5, and times L, and that gives us a length of 2.31. Let us put it nicely. 2.31 meters. Finally, let us go to our last example, and the example reads: air is to be, no, not that one, but this one here, that reads: a counterflow double pipe heat exchanger is to heat water from 20 degrees to 80 degrees at a rate of 1.2 kilograms per second. The heating is to be accomplished by geothermal water available at 160 degrees C at a mass flow rate of 2 kilograms per second. The inner tube is a thin-walled and has a diameter of 1.5 centimeters. The overall heat transfer coefficient of the heat exchanger is 640 watt per meter squared Kelvin. You're told, using the effectiveness NTU method, determine the length of the heat exchanger required to achieve the desired heating. Now let's go to our let's have a look at the solution. Always in NTU method, first thing we do is calculate the heat capacity rates. So let us have a look at what SCH is: mass flow rate of the hot times the CP of the hot stream, which is equals to 2 times 4.31, which is 8.62 kilowatt per Kelvin. CC is m dot C CP C, which is 1.2 times 4.18, which is equals to 5.02 kilowatt per Kelvin. So we can deduce, or we can see, that CC is equals to C minimum, and it is equals to 5.02 kilowatts per Kelvin, and CH is equals to C maximum, and it is equals to 8.62 kilowatt per Kelvin. Now we are armed with the two capacities. Can go ahead and calculate our times TH1 minus TC1, and that is equals to 5.02 times 160 minus 20, and that is 702.8 kilowatt. Now Q is equals to mass flow rate of the cold, Cp cold, Tc2 minus Tc1, which is equals to 1.2 times 4.18 times 80 minus 20, and because Cp is in kilo, the answer will be kilowatts, and that is equals to 301 kilowatts. Now our epsilon, the effectiveness, is equals to 301 divided by 702.8, which is equals to 0.428. And know that this is a counterflow. Exchanger. So we can go ahead and calculate our NTU, which is equals to 1 over R minus 1 ln epsilon minus 1 divided by epsilon times R minus 1. And that is equals to 1 over R minus 1. We didn't calculate R minus 1 ln of 0.428 minus 1 over 0.428 R minus 1. So what is our R? Our R is equals to C minimum divided by C maximum, which is equals to 5.02 divided by 8.62, which is equals to 0.582. So our NTU is equals to 1 over 0.582 minus 1 ln 0.428 minus 1 over 0.428 0.582 minus 1, and that gives us a figure of 0.651. But we know that NTU is equals to UA divided by C minimum, which implies that A is equals to NTU times C minimum over U. Okay, so it implies that our A is equals to 0.651 times 5020 divided by 640, and that is equals to 5.11 meters squared. but the heat transfer area is pi times d times the length of the exchanger. So that is equals to 5.11. So pi times a d times L is equals to 5.11, which gives us a length of 108 meters. Thanks.